Partial sums of a sequence. So in calculus, we're often interested in adding the terms of a sequence together. So this is going to lead to this, this definition where we have partial sums. So for the sequence A1, A2, A3, A4, and so on, the partial sums are really just adding the previous terms together. So first sum is just the first term. The second sum is the first and the second added together. The third is the first, the second, and the third. The fourth is the first, the second, the third, and the fourth, and so on. So by the time we get to Sn, S sub n, we've added all of the terms together. Okay. So S sub 1 is called the first partial sum. S sub 2 is called the second partial sum, and so on. So it's the nth partial sum by the time we get to S sub n. And this sequence is called the sequence of partial sums. They didn't really, reach too far with a name there. All right, we want to find the first four partial sums and then the nth partial sum. All right, so in order to do this, what we need to do is at least find the first few terms. Okay, so in order to find those first four, we're going to find what are the terms in this sequence. Okay, so we have 1 over 2 to the n. So if we plug in 1, that's going to be 1/2. If we plug in 2, that's 1/4. If we plug in 3, that's 1/8, and so on. Okay, so the first sum, the first partial sum would just be the first term, so 1/2. The second partial sum should be 1/2 plus 1/4. So we're going to get 3/4, so 1/2, 3/4. The third partial sum should be 1/2 and 1/4 and 1/8. So that's going to give us 7/8. Okay. The fourth partial sum, we have 1/2, 1/4, 1/8. This would give us 1/16 as the next number. So that is going to give us 15 over 16. Now to generalize this to the partial sum for the nth term or the nth partial sum, we need to just sort of look for a pattern within these partial sums here. Okay, 1 over 2, 3 over 4, 7 over 8, 5 over 6. So the first thing we want to figure out is where did the 2, 4, 8, and 16 come from? And that's really coming from right here, that 2 over n, right? 2, 4, 8, 16. Okay, so we know the denominator, right? We know it's 2 to the nth. Now we just need a numerator. Well, it looks like it's 1 less than the denominator. So we can say that's just 2 to the n minus 1. Okay. We could also simplify this a little bit. So if you wanted to, you could just divide both those top terms. So 2 to the n over 2 to the n minus 1 over 2 to the n, and then just say that's 1 minus 1 over 2 to the n. This is perfectly acceptable, but so is this answer. So whichever you'd prefer. All right. Find the first four partial sums and then the nth for this sequence. All right, so let's think about what are those terms. So if we plug in 1, we're going to get 1/2 minus, let's see, if I plug in 1, not 2. If I plug in 1, so a sub 1 is going to equal 1 over 1 minus 1 over 1 plus 1. So that's going to give me 1 minus 1/2 or 1/2. If I plug in 2, that's going to give me 1/2 minus 1 over 2 plus 1. So 1/2 minus 1/3, which will give me, well, let's see where that takes us. Okay, so we know S sub 1 is just adding the first term to itself. So we're going to have, like we said, 1 over 1 minus 1 over 1 plus 1. So 1 over 1 minus 2. And then we're going to get 1/2 here. Okay. S sub 2, we're going to add the first term and the second term together. So that's going to be 1 over 1 minus 1/2 plus 1/2 minus 1/3. Okay. All right. Well, these are going to cancel, and I'm really just getting 1 minus 1/3, so I'm going to get 2/3. Right, S sub 3. We have the first term, the second term, the third term. We've got 1 over 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. You can probably start to see the pattern here. The halves cancel, the thirds cancel. I have 1 minus 1/4. That gives me 3/4. So S sub 4, we're going to get the first term, the second term, the third term, and the fourth term all added together. That's going to give us 1/1 minus a half plus 1/2 minus a third plus 1/3 minus 1/4 plus 1/4 minus 1/5. These are all going to cancel out in the middle, and we have 1 minus a fifth. We'll get 4/5. So now we want to find the fourth partial sum. We need to look for a pattern here. So for our pattern, it looks like every time it's going to be 1 minus, right? 1/1 minus, 1/1 minus. So 1 minus, it was 1/2, 1/3, 1/4, 1/5. So 1 more on the bottom. So 1 over n plus 1. All right. So then we have something called sigma notation. We saw this a little bit with statistics. So the Greek letter sigma, it's now the capitalized version. Lowercase sigma is this one. So this is lowercase. We want to talk about the uppercase sigma. This is the one we're talking about. It really stands for the sum. It helps us to add things together. It's a shorthand. Okay. So we saw in probability, we said the sum of like x times p of x. And that just meant add up all of the x's times p of x's. Same kind of concept here. So given the sequence, we can write the sum of the first n terms using sigma notation or summation notation, just like the word sum. And we use that capital sigma there. So here is, our sigma. We're adding up all of the a sub, and then in this case we put k's, and we want k to go from the number 1 up until the number n. So the left side here is reading the sum of a sub k from k equals 1 to k equals n. The letter k is really what we're calling the index of the summation or the summation variable. It's telling us basically what numbers we are going to add up. What are we putting in there each time? All right, so here we want to find the sum of each of these. So we want to find the sum when k is 1, 2, 3, 4, and 5, all the way up. So we will have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. And what I've done is replace the k each time with those numbers from 1 to 5. All right, so let's see. 1, 4, 9, 16, 25. And then it's just simple arithmetic here. When I add, I'm going to get 55. Okay. For the next one, same kind of concept, but we're going from 3 to 5. So 1 over 3 plus 1 over 4 plus 1 over 5. And in our calculator, that's going to give us 47 over 60. Okay. The next one, we're going from 5 to 10, just plugging into I. So 5 plus 6 plus 7 plus 8 plus 9 plus 10. That's going to give us 45. Okay. Same kind of concept here. When I is 1, well, there's no I. When I is 2, when I is 3, when I is 4, when I is 5, and when I is 6, we're going to get 12 there. There wasn't an I to plug in, but I do need the equation for each of the different I's that we have. Okay. So let's take a look. So we can write using sigma notation. We can kind of go in reverse. So we see what's changing each time. 1, 2, 3, 4, 5, 6, 7. That's what we're plugging in really, and it's being cubed. So we can say we're taking the sum from when k is equal to 1 up until the number 7. That way we use each of those. And it looks like the pattern here is k is being cubed. Okay. For the next one, I'm seeing what's changing, 3, 4, 5, all the way up to 77. So we're starting at 3 and we're going up to 77. And what is the operation that's happening to those numbers? It's being square rooted. So we can say the square root of k. All right. The following properties are natural consequences of the properties of real numbers. So we see when we have the sequence of A's and the sequence of B's, they're two different sequences. Every positive integer n and any real number c are going to hold the following properties. So if I am taking the sum of all of the A's added together plus all of the B's added together, It's the same as adding all the A's first and then adding all the B's. Okay, so it's really just kind of putting parentheses around it. It's saying, okay, add these up first and then add these and then add those sums together. We can add in any order. That's really what's happening here. Here, if I'm doing all of the A's minus all of the B's, I could do all the A's first, all the B's together, and then subtract those. Because really think about it. This is like saying A1 plus A2 plus A3 plus, and then minus B1 minus B2 minus B3. If I'm doing that, really it's like factoring out a negative from the B's and then saying this is all the A's minus all of the B's. Okay. And then down here, if we just have a constant number, that's what C is. It's a constant, just plain old regular number. If I factor that out, if I pull it out, because A sub K, this sum here is just saying A1 plus A2 plus A3 and so on. Here I'm saying, and I'm multiplying it by C. Here I'm saying C times A1 plus C times A2 plus C times A3 and so on. This is really just factoring out a GCF. Okay, so all of these rules are really the same as our regular real number properties.